And I'm Alessandro Trinca. I'm a current postdoc at the Astronomical Observatory of Rome. And today I'm going to give you a brief overview of the work that we're doing in trying to exploit the synergy between small-scale hydrodynamical simulations and semi-analytical models in order to investigate the role of supercritical accretion in the growth of the early population of AGNs that we're starting to observe with JWST. Now, as we heard already before the break, and as you would probably know, JWST already improved drastically our knowledge of the high redshift universe, and especially concerning the population of highly accreting black holes. And we had more than 40 detections of AGNs up to redshift 11. And as you can see, basically, we're starting to probe not only the very high redshift, but also the region of less massive and fainter black holes, going down to black hole mass around down to 10 to the 6 solar, and so starting to probe what we think is the regime where black hole seeds, heavy black hole seeds, are formed. Now, many of these systems have the peculiar seems to show a very peculiar feature, which is the fact that the black hole is supermassive with respect to the stellar component, and this might be, of course, an observational bias, but it's giving us some hint that a brief phase of supercritical or very efficient accretion is needed in order to build up these objects. And for this reason, basically, this population of AGN is very promising to study the early mechanism of black hole formation and growth. In order to study this scenario, we developed this cosmic archaeology tool, which is a semi-analytical model designed to reconstruct the early coevolution between galaxies and AGNs at high redshift, and which is characterized by a very detailed environmental dependent seeding prescriptions for both for light and heavy black hole seeds. And basically, the strength of this model is that we're able to provide easily large statistical samples of the galaxy and AGN population down to redshift 4 and provide catalogs for different potential evolutionary scenarios for the black hole growth. And basically, it turned out that this model has a very high predictive capability, since you can see in the bottom panel how our predictions for the population of faint AGNs is very well matched by the first confirmed first estimates coming from JWST detection of this fainter population of AGNs around redshift 5. And you can see that from the comparison from the prediction, which are the black dots and these reddish and violet estimates in the right part of the plot. And we used this model lately to see what is the actual impact of different potential accretion histories in the building up of the population of massive black holes, and in particular on the black hole mass function. And you can see here on the left, the evolution of the black hole mass function from redshift 18 down to redshift 4. And you can see how basically, assuming a standard Bondi-Hoyle Eddington limited scenario, what we can call the high mass end of the distribution is built up basically on heavy seeds, since lighter seeds are not able to grow efficiently across cosmic times. While if we enable the nuclear black hole to grow, even for a very small period of time of the order of one or few million years at super Eddington rates, during major galaxy mergers, you can see how this gap between the two populations is actually bridged, and light seeds are able to contribute significantly to the building up of the high mass end of the distribution. And to try to disentangle between these different potential accretion history, we have to go either very deep, let's say, so try to constrain the properties of very less massive black holes, or to go at higher redshift, where you can see that above redshift 8, the two distributions start to change drastically. But luckily, JWST seems to enable us to go in both directions since we had, as we heard before, the first detections of AGN candidates at redshift higher than 8, spanning from masses as high as 10 to the 8 down to 10 to the 6 solar. And as you can see, and as is stressed actually very well in all these figures, these systems are crucial to try to uncover and put some constraint on the early mechanism of growth of these early massive black holes. And prompted by this detection of faint AGNs with JWST, we perform an extended comparison between this population of systems and the synthetic catalogs that we produced with the cosmic archaeology tool for both the accretion scenarios. And what I'm showing you here is basically the black hole mass versus stellar mass relation for the two models, where all the big points that you see are the JWST detections, and they're compared with this population of yellow dots, which are our candidates, where we highlighted the population of systems that we expect to be observable with different surveys, and in particular with CHEERS and JADE survey. And as you can see, basically going to higher redshift with just a few detections is very difficult to have some strong smoking gun for one of the other accretion scenario. But the point is that, as you can see, the number density of plot that you see is very different. So you expect to have some basically large differences on the number of this kind of object that you expect to be able to see at this high redshift. While if you go at lower redshift, you see how around redshift 5, the fact that you're starting to see a population of overmassive black holes with respect to the galaxy component might be a strong signature of the fact that this system might experience some at least brief period of enhanced accretion during their early growth. And of course, the different accretion history does not impact only the scaling relation, but also a lot of other properties of the galaxy and the AGN population, and in particular the observability of the system, since you expect that highly accreting system might be observable up to higher redshift, but also the spectral signatures of both the AGN and the host galaxy. And on this, you will hear a more detailed description in Rafaela Schneider's talk on Wednesday. But what I want to stress out here is that a proper modeling of this brief period of enhanced accretion is crucial to try to extract as much information as we can from this few detection at very high redshift, and still our understanding on the condition enabling this potential to Reddington growth is limited. So we want to rely on high resolution hydrodynamical simulation to try to exploit the synergy between them and semi-analytical models. And concerning that, in my group, basically in this work, some hydrodynamical simulation on very small scale has been performed, investigating the accretion on a 10 to the 3 solar masses black hole in the inner region of a very gas-rich and metal-poor galaxy at high redshift, around redshift 15, using the SPH code gasoline 2. And what they actually see is that from the start of the accretion in a timescale of the order of 1 mega-year, we have a rapid quenching of the black hole accretion due both to black hole feedback and star formation. And depending on the potential feedback model that they assume, the growth of this initial small seed might reach up to 10 to the 4 solar masses in a very brief period of time. Now, what one can do is just to extrapolate this growth down to lower redshift, assuming that a sequence of major events are able to replenish the inner region around the black hole of gas. And extrapolating this evolution, one can see that the maximum mass that you expect to reach a redshift 6 is of the order of 10 to the 6, 10 to the 7. But what we can actually want to do is to combine this information with the hierarchical growth that is predicted for these light seeds from the cosmic archaeology tool. And so we want to to combine a suite of simulation coming from small-scale Iso resolution simulations with the evolutionary track that you see here for this population of light seeds in order to properly model this brief period of enhanced accretion. But in order to do that, we need to probe this enhanced black hole growth over at least a wide range of initial black hole masses. And for this region, what we are currently doing is to performing several simulations spanning between 10 to the 3 initial solar masses for a black hole up to 10 to the 5. And you can see here how the gas density evolves in a time scale of the order of 1 mega-year for the 3 systems. And what we want to obtain with this kind of simulation is to estimate which is the time duration expected with the dependency on the black hole mass potentially, and what is the maximum mass growth that we can have in this brief accretion episodes. And in particular, we want to study which is the impact of the black hole displacement, since you expect lighter seed to be harder to keep at the center of the gas reservoir, but also of star formation and feedback on the overall evolution of the black hole. And this will enable us to provide a more detailed modeling of this accretion episode, and therefore more accurate AGN catalogs that together with, for sure, the availability of more detection from GWST will allow tighter constraints on the evolutionary scenarios of these first massive black holes. So stay tuned. This is all I have for you today, and I'm taking questions. Thank you.
Questions?
Yeah, this is great. Thank you. So how super Eddington can they go, and for how long does that happen?
I mean, looking at some preliminary results, it seems that for this brief period of time, which are always of the order of a few mega-year, they can reach up to 10 to the 4 Eddington. So they can accumulate a lot of mass, actually.
You have feedback?
We have feedback, but just thermal feedback. We are planning to extend this suite of simulation also with Gizmo and applying a more detailed treatment of biconical feedback and momentum driven. So for the moment, it's just thermal feedback.
Do you have the drop in the radiative efficiency?
We have, for this simulation, we actually fixed the, I mean, there is a dependency. Yeah, we fixed the radiative efficiency and explore how the total growth of the black hole changes depending on that, using 2 models of coupling and feedback for the feedback. Yeah.
Thank you.
Other questions for Alessandro? This is good. I can work off my lunch.
So my question is related to the dynamical stability of light seeds. So you said that with the mass of a few hundred solar masses, does the black hole accrete just randomly from streams of gas that get close to the black hole, or is the black hole located where the gas goes to it? So in other words, does the black hole stay fixed at the center of the potential well of the halo, or it goes around and randomly encounters dense streams of gas?
We start to see a dependency of the initial black hole mass since the 10 to the 5, as you can probably see a little bit here. I don't know if it's working. But I mean, the more massive black hole stays at the center of the halo, and it has a larger availability of gas, while the smaller one are more subject to wandering around. The point is that we want also to try several realization of this to see if it's just, I mean, statistically, the smaller black holes will wander around much more, and this impacts a lot the initial growth. However, it seems that even in this case, they manage to accrete a large amount of gas in this brief period of time, because the smaller one accretes are of the order of 10 to the 4 solar masses in just 1 mega-year. And this might be enough, probably we have to see that, but we have to check that, but in the overall hierarchical evolution is already some positive information for bridging this gap between POP3 remnants potentially and more massive black hole seeds.
So very quickly, but here you set up an idealized galaxy with a smooth potential.
Yeah.
Okay, thank you.
Quick question.
Quick question here. So 10 to the 4 solar masses that are being accreted. Is there a cap to the available gas that is available in this, I guess, in this gas or in this galaxy or halo? Or is this like an infinite amount of gas that
yeah, sure. For this kind of simulation, we just kept the same initial condition concerning the amount of gas. We have of the order of 10 to the 6 solar masses of gas in the in the exponential disk, and we do not have replenishment because we are just studying these brief periods of enhanced accretion, and we want to apply that to the hierarchical growth in mergers of these seeds.
All right, thank you so much, Alessandro.
Thank you.
I have no idea how to do this.
I have no idea. I just pressed escape on the keyboard. Then you have to move the mouse, which is very terrible.
And Doug's like, I'm so glad I'm not the one doing this.
That's right.
Okay.
The last one.
Okay. Oh, there we go. It's a terrible mouse. Oh, I change the name of your thing.
Is it opening in the PowerPoint?
I don't know. Is it?
No, I don't think so.
It doesn't seem like it wants to open.
Let's just press.
There we go.
Okay.
Okay. So I'll give you a 2-minute warning after 10 minutes. Okay.
Okay. Hello, everyone. It's a pleasure to be here today. I first want to thank Doc and Sophie for organizing this conference. Otherwise, I would know nothing about galaxy formation. Oh, yeah, sure. So today I want to talk about a new theory for hot accretion flows within the boundary radius. So as we all know, galaxy formation is a multi-scale problem. We have many orders of magnitude between the event horizon all the way to galaxy scale and even all the way to cosmological scales. And for this talk, I want to focus on the smallest scales of this problem, which is when we have the hot accretion flow within the boundary radius. Now, one comment here is that these numbers here are just based on one particular system, M87. It could change by a lot between different galaxies. There might even be cases where you don't have a hot accretion flow at all, where the hot accretion flow doesn't matter. So this talk is really limited to the case when you do have a radiatively inefficient accretion flow dominating your accretion. And the question I want to answer is how to model this radiatively inefficient subboundary accretion flow. And from observation and past simulations, we do seem to have an answer already. That is, this kind of flow tends to develop a self-similar profile with a density slope somewhat close to -1. So here in this plot, I'm showing you some simulations for the accretion onto Sagittarius A star by Sean Ressler et al. Also in comparison with a bunch of different observational estimates, you can see they are broadly consistent with each other. Similar results are found for M87 star, as Minghao talked about earlier in the morning. And an interesting trend that appear among the simulations is that this slope seems to be quite universal. You get qualitatively the same result and basically the same slope with and without magnetic field, with and without realistic cooling, and with and without any large scale rotation. So that seems to be a puzzling behavior. What is even more puzzling is that no theory predicted this slope before. So if we look at the original boundary accretion or boundary Hoyle accretion, basically there the assumption is you have constant mass flux in order to conserve mass, and you end up with a slope of -1.5. Then if you look at solutions like CDEF, the requirement of constant energy flux give you a slope of -0.5. There are also other models that just treated the slope as a free parameter, but really nothing has predicted -1 before. And this basically led to this work I published earlier this year, trying to have a new theory for this type of -1 slope. Following the tradition of 4-letter acronyms, this is called simple convective accretion flows, or SCAFs. So the first thing I did was to try to give a minimal example of this SCAF flow. As we have seen earlier in previous simulations, this thing seemed to appear no matter what, so I decided to just go for the simplest case possible, which is to start from some static uniform medium with pure hydrodynamics, adiabatic equation of state, gamma 5/3. Let's just throw in a accretor and see how it evolves. Although realistically, we also need to make sure this thing runs within a mesh. So we also throw in some outer boundary, add a radius comparable to the boundary radius, and put a damping zone further out. These simulations are done using the code Athena++. These are 3D simulations with mesh refinement just to ensure good resolution at all scales. And I surveyed a range of different scale separations. So if you just run this simulation as is, of course, you will just get a boundary flow because you have exact spherical symmetry in your initial condition. But what's interesting is if you just inject a tiny bit of perturbation, in my simulations, it's like 5% sound speed, initial turbulent kick, the flow develops into a completely different state. You get this kind of large scale self-similar turbulence. Here, the first panel is showing dynamics around the boundary scale, and the other panels are zoom-ins. This is the same snapshot, just plotted in polar coordinate and in a logarithmic R scale, just to show you that these velocity structures, these turbulent rolls, are roughly self-similar. And here is a more quantitative view of the simulations. Each column here is a different simulation. I'm showing the spherically average radial profiles. And as you can see from right to left, we have increasing scale separation, and we do see the trend of converging towards a self-similar steady state. What's interesting, though, is that this steady state doesn't seem to have a slope of exactly -1. In fact, it looks more like R2 minus 0.8. And when I went back to look at the other simulations, including some of my own simulations, I did find that what we claim to be a -1 is usually consistent, if not better fitted with a -0.8 slope. And we chose the -1 only because, you know, people like integers. So, all right, so with this simulation, we get a basic qualitative and quantitative view of the SCAF flow. And that also highlights a few questions. The first question is what drives this large scale turbulence? And the second question is what sets this -0.8 slope? And finally, as I mentioned earlier, the slope seems to be quite universal. Why is that? So in order to answer this first question, the easiest way to do it is to look at the energy budget. If you do some math, you will see that the rate of change of the kinetic energy, you can decompose into different terms. You don't have to memorize the expressions here. It's no longer your graduate school fluid dynamics class. But the idea is just you can do this decomposition and you can measure each individual term in the simulation. And at the end of the day, what we found is that the dominant source of kinetic energy injection is due to this buoyancy term. In other words, this turbulence is driven fundamentally by convective instability. So that's why we have this term of simple convective accretion flows. Really, it should be called convection-dominated accretion flows, but the name is already taken. Okay, so moving on to the second big question, why this -0.8 slope? Well, here things get a bit more tricky because we have to look at the momentum equation. So the momentum equation can be rewritten, roughly speaking, as two terms. One is the divergence of turbulent energy flux. The two is a mean acceleration term. And the divergence can be further rewritten in terms of this density slope alpha rho if you assume self-similarity. So that gives you alpha rho equals to -1 plus this messy looking thing. What we're going to argue next is that this second term is actually small. And there are two reasons that contribute to this. The first is that our flow, because it consists of highly turbulent convective turbulence, there is an approximate up-down symmetry there, meaning that when you drive out, when you drive bubbles moving out, you also drive bubbles moving in. And that means if you look at the average acceleration in the flow, it's going to be less than the typical acceleration. And the second part that goes into this argument is that the convection is relatively strong. So the mixing length or the characteristic scale of the velocity rolls, those are comparable to the radial scale. So the bottom part here, the VR squared over R, that is actually comparable to the typical acceleration. So we have the top part being much smaller than typical acceleration and the bottom part being comparable to the typical acceleration. And we thus conclude that alpha rho needs to be -1 plus some yet unknown small number. So this is an interesting argument because I think this is probably the first time the slope is derived not by like exact conservation law, but just some approximate symmetry. And that's why we get this weird 0.8 slope. The same argument also explains why the slope is so universal, because now we can use the same argument. We can still use this argument of mean versus typical acceleration, even when we add in more physics. For example, if we have some magnetic field, you will of course change the expression of the acceleration, but you can still do this decomposition of of divergence of momentum flux plus mean acceleration, and you can redo this whole analysis as long as you still have this large scale turbulence with approximate up-down symmetry. A very extreme example of this is that this might actually be a way to explain the scaling of magnetic arrested disks, or MAT. So I forgot to put a reference here, but there's a recent paper by Mitch Begelman et al. They were arguing that in MAT, you basically get a convection-like instability where you have a lot of interchange. And if you apply the same argument, you do seem to explain why MAT simulations also find a density slope that is close to -1. And in conclusion, now we have a theory of this simple convective accretion flows that agree with observation. So the simplest check we can make is to predict the dependence of the dependence between the accretion rate and the scale separation. Basically, if you normalize your accretor size and accretion rate both by the corresponding boundary radius and boundary accretion rate, you'll find a slope of around 0.7, and that agrees fairly well with the two supermassive black holes we know well of, Sagittarius A star and M87 star, and also a bunch of wind-fed supergiant X-ray binaries where the neutron stars might also be accreting from a similar type of flow. And hopefully in the future, we'll see more observations populating this gap in between. And I want to end by quickly talking about some work in progress. So right now, working with Yixian Chen, who's a graduate student at Princeton, we are starting to give a more systematic survey of flow morphology, see how the qualitative flow morphology as well as the radial slope changes as a function of both scale separation and the level of upstream or large scale rotation. There are already a bunch of different regimes, some we know of like boundy and scav, some we don't quite know yet, like the green region there, we see something that looks kind of like a CDAV, but it also has very strong Muradonial flow. So this is something you should probably hear more about next year. Okay, so I will leave my takeaway here and I'll be happy to take any questions.
Thank you very much for the talk. I was wondering that since it's also pretty stable, but for this case, in the around, I think there should be a cut where your flow is not self-similar because of the strong gravity, right? So
Right.
what do you think will be the cut?
Yeah, so this is a really good question. I cannot put a precise number to it, but just in terms of scaling analysis, it should wait, are talking about the part where GR starts to matter, or the part where the self-gravity of the galaxy starts to matter?
Yes. And another question is that, so since the mean acceleration is pretty small, I'm still thinking whether this kind can be think as kind of like conservation of radial momentum flux.
Yes and no. The no part is mainly because if you do the say if you take the momentum equation, when your turbulence is weak, then the divergence of turbulent momentum energy doesn't matter, and you cannot enforce the flux slope there. But when the turbulent momentum energy is strong, there's no longer an obvious reason why your mean acceleration should be close to zero. So that up-down symmetry argument I mentioned earlier actually cheated a bit there. If you want a more like quantitative argument, there's a 2-3 page appendix in my paper that you have to go through. But yeah, it's not obvious.
Yes. And then one last question is that, as I remember you mentioned in your paper that it slightly depends on the inner boundary, right? So
yes.
I'm not sure that what kind of inner boundary might be more realistic, but of course, depending on the exact system. So could you comment more on that part?
Right. That is a great question. Here, qualitatively speaking, we can say when the scale separation is large enough, say when we have 3 or 4 orders of magnitude of scale separation, the exact choice of the inner boundary doesn't matter as much. But when you are at a regime where you're like only marginal to say this transition between boundary and scab, this exact boundary could depend on the details of your creature.
Yes, we think.
Are there any additional questions?
Really, really interesting. I'm sorry, I missed something very basic here. So how would you basically summarize the difference between the SCAF and the CDAF?
They have different slope, and CDAP also assumes a disk-like morphology that is only marginally convectively unstable.
Whereas you're convectively dominated.
Yes.
Okay, let's thank Wenwu again. So we now have 4 rapid talks. So these are going to be 5-minute talks, and the idea is mostly for you to learn about the exciting research that these people are doing so that you can go and talk to them and get more details. So we're going to hold the questions until the very end. Hopefully we'll have a little extra time at the end when you can ask questions of any of the speakers. But for now, we're just going to barrel through the 4 talks. So Brian, please go ahead.
Sure. So I'll be talking a little bit about my work, which looks at how black holes co-evolve with their host galaxies. This is black hole mass, stellar mass relations. So I'm just going to be talking about how galaxies evolve on this space. And then if I have time, talk about how short-lived black hole feedback events, like in the movie I show here, affect galaxies in the long term at giga-year scales. So basically, black hole growth histories are really useful to know, and we want to know more about them, but it's really hard because physically we are the constraints are very hard to get. And so here in my work, I kind of use an empirical approach. This is really useful because we want to be able to understand what the observations are telling us about how these black holes grow. So basically, how I do this is I take an empirical model of galaxy formation and I build black hole growth histories on top of that in post-processing. And I do this by assigning all galaxies within the universe machine at redshift 0 a black hole mass based on the observed redshift 0 black hole stellar mass relation for quiescent and star-forming galaxies separately. And then I also assign the black hole accretion rates based on the probability distributions of black hole accretion rates as a function of galaxy properties. And so just to go through this, I separate the galaxy population in the universe machine based on whether they're star forming in blue or quiescent in red. And I also split them into 5 different star formation rate bins. Starburst, main sequence, sub-main sequence, and then 2 for quiescent. And then I assign black hole masses at redshift 0 in the universe machine based on the observed relationships. Here's my points from my 2017 paper, and then Jenny Green's points, or Jenny Green's relations in red and blue. And then I assign black hole accretion rates based on these data here. These are probability distributions for the 5 bins of star formation rate in different redshift bins here. And basically, I select from the distribution to attach a black hole accretion rate to each galaxy. And then you can iteratively calculate the growth histories between redshift 0 and 2 and obtain these black hole galaxy scaling relations at high redshift. And what you can see here, one of our main results is that the separation between quiescent and star forming galaxies that we see at redshift 0 basically goes away by redshift 0.5. And also another thing is that it's really hard to grow massive black holes, and it's a lot easier to grow lower mass black holes. So here, the quiescent galaxies at redshift 0 that are overmassive are very difficult to grow, so they've grown very early. And then those galaxies that are star forming at redshift 0 have grown very recently. And so this might be limited by stellar feedback, as we heard many times, and then grow later in time. Whereas these earlier, these galaxies with massive black holes might have grown a lot earlier in the early universe. I've also done some work on short-lived feedback and whether that affects the evolution of galaxies in the long term. Basically, it absolutely does. It affects the circumgalactic medium around galaxies in various ways by increasing entropy, increasing these vents that are above and below the galaxy. And then also it makes stellar or gas, radial gas, the central gas density is a lot as much suppressed, and so that persists like 800 million years into the future after the actual black hole event. So that's what I got. Thanks.
All right. Come on up. These all in one file by any chance? No?
Good question. Maybe.
That would have been smart, but
No, I don't think
doesn't
so.
look like it.
For tomorrow.
Yeah, that would be a good idea for the rapids. Especially given
The mouse.
okay. You can probably work this just as well as I can, if not better. So
come on, there you go. Okay, so good afternoon. My name is Jonathan Mercedes Felice. I'm a PhD candidate student at the University of Connecticut, where I do work with Daniel Anglazalcazar, specifically looking at Asian feedback. I'm going to go kind of really quick, go through my kind of 2 papers where I have the QR codes on the top left and right. So kind of what's the whole thing about my 2 projects? Essentially, we're looking at so essentially negative Asian feedback is a necessary process, is a crucial role in order to kind of, reproduce observational data, which shows that we need some amount of feedback in order to shut down star formation and allow us to essentially quench these massive galaxies. However, in the past decade or so, there have been some observations as well as models where they propose positive Asian feedback. So instead of quenching massive galaxies and shutting down star formation, you're actually triggering star formation by compressing gas to higher densities. So what we do is we essentially try to further study this dual role of Asian feedback using the FIRE simulations, which stands for feedback in realistic environments, where I have this massive galaxy at the redshift 2. We have a suite of simulations where we introduce Asian feedback in the form of winds with this new wind particle spawning technique. And so what I have real quickly down here is just looking at these spatial star formation rate surface density maps for the no wind on the top and for the Asian wind case on the bottom. You can essentially see that overall, there's a global negative impact due to the Asian winds. However, we do see some signatures of positive feedback in the local scales. So we look at essentially three different signatures. First one, we see essentially higher star formation rate surface densities within certain radial ranges when we compare the no wind, which is the blue line, and the Asian wind as the orange line. We also see that within, along the edges of the cavity, we see higher star formation efficiency, which we see really well in the radial profile on the bottom left. And then ultimately within the Asian wind simulation, we also find that there is higher amounts of star formation in outflowing material than inflowing. Now we kind of look further into kind of another form of local positive feedback, but this is occurring at simulations with much stronger feedback winds. So what I have here is essentially looking at the stellar surface density maps of a whole suite of simulations. So we go from no Asian wind on the top left, and as we go down, we're increasing Asian winds. And we essentially find these dense, ultra dense stellar clumps. So particularly the one I focus in the paper is this clump A, which we essentially notice that this clump is forming in much higher density gas, as opposed to the overpopulation of stars that form within the same 35 million year presence. And we also see that essentially this clump is forming much faster if we just assume gravitational effects. So essentially the Asian winds are allowing the gas to compress to much higher densities and collapsing much faster than radiative feedback. So this is just a movie essentially showcasing the evolution of this clump. And the green gases, the green points are gas particles. And as you see, as the Asian winds are propagating out, we're compressing the clump into these very small region, and then immediately starts forming into stars. And so this is happening in less than 5 million years, which is essentially right before radiative feedback has enough time to essentially disrupt the gas and essentially not allow for the clump to form. And I think I'm good on time. I'm just going to show my summary slide. And both my 2023A and 23B paper are outlined there in QR codes. Thank you.
Zumani, come on up.
Oh my God.
I'm getting better at this. She's not saying much. Money, I'm gonna let you start it yourself. Okay.
I couldn't decide on the title. I got too stressed out, so it's just my name.
Nice pattern.
Oh my goodness, where's everything at? What's wrong with this mouse?
Oh no.
Okay. Hello everyone. Nice to see everyone. So my name is Amali Dindi, as you can see. I'm a master's student at the CUNY Graduate Center. I work with Ari Maller. And so we're really just focusing on what drives black hole mass in the illustrious TNG simulations. We're looking at the properties from the galaxies in them. That's basically what we're doing. So I just wanted there to be like 4 major takeaways so far. Okay, it works. Okay, so one, it looks like we found like a resolution issue in 100 and 300 boxes, which is pretty interesting. 2, we did find an acceptable black hole mass model using only 4 features in the from the galaxies themselves. 3, so we also tried a symbolic regression on all 3 boxes, but it failed majorly on the 50, which is weird. And then also we find that the 100 and 300 boxes don't really relate to one another, which is also kind of weird. So yeah, so we're gonna get into that. Yeah, okay. So like I said, we worked in the TNG 50, 100, and 300 boxes, just looking at Redshift 0. And so we started with 12 features. And so as you can see, we used a random forest machine learning model. We also used support vectors and a neural network, but they basically look the exact same. So I just was going to show the random forest today. But just with that alone, you can already see something kind of off with the 100 and 300. Like you have this like higher mass black holes, and they're like pretty well correlated. And then the lower mass kind of just a blob there on the screen. So initially we thought, well, maybe our model is just catching something in the higher mass regions and not the lower mass regions. So we decided to split them up and then run it on the lower mass by themselves. That didn't do anything, so we had to try something else. That something else was we chose to divide out the gas resolution elements. And in doing so, you see that this lower mass issue that we were having, they basically line up. So it's like pretty clear evidence that it's a resolution issue between the two. So using that, we decided, okay, well, we can just cut from there, and that lines up to be about 10 to the 7 solar masses and above for TNG 100 and 10 to the 8th for 300. So then you get these like nice true and model predictions, which is pretty great. And then so from there we decided, okay, well, we have these decent scores. What features from these galaxy properties are actually causing these like relations with the black hole mass? So we see that with just 4 different features from these different simulations, we can get basically the exact same score for them. So that's also kind of interesting. So we went from 12 features early on to just 4 now. So now we thought, okay, well, we can use those 4 features and then just toss them into our symbolic regression and see if we can get like an equation that easily captures the black hole mass with these 4 properties. That's heads up. Like I said earlier, okay, the TNG 50 did not work whatsoever, so I didn't even bother putting that up there. But for the TNG 100 and 300, we see that for the 100, we get 2 relations of features that we have, 2 features that we have in these equations. And then for the TNG 100, we get just 1 feature, which we thought that was pretty interesting too. And they do quite well when used on the box, their own respective boxes. But considering that these simulations are basically trying to do the same things just at different scales, they should be able to be interchangeable. The equation should be able to work on different boxes. But we actually don't see that quite well. So the fit that we got for the 100, actually, it does pretty decent on the 50, but it doesn't do too well with the 300 box. And then with the 300 fit, we don't see anything good with the 50 or the 100. And so that's basically where we are at now. And so that's all I have for you today. Thank you.
Perfect timing. Thank you. Last speaker of the rapid session is Megan Tillman. You want to wrestle with the yourself? It'll be nice.
We just need a mouse pad or something.
Maybe. Tomorrow. We should talk about it.
The mouse?
Yes, bring over my mouse pad from my office. I could try that.
Apparently it's a problem.
Oh, really?
They know. I can tell.
All right, so we've been looking at a lot of small scales and a lot of intermediate scales for black hole feeding, accretion, feedback. I'm going to take us to the largest scales possible with the IGM, and we're going to look at AGN feedback effects on the low redshift Lyman alpha forest. Sorry, this talk isn't with the rest of the feedback talks. I will not be here tomorrow. So first, a little overview of the low redshift Lyman alpha forest. It's basically the neutral hydrogen in the IgM in a certain column density range. And at low redshift, we have consistently seen mismatch between the Lyman alpha forest column density distribution that is predicted by simulations versus what we see observationally. So there are many ways that we could resolve these differences. Basically, you need either photons or heating, but as you can see in this plot, that black line is some of the gadget simulations, and you can see when compared to the observations, which are the pink points, you really do not have a match there, and you need to correct the UVB by a factor of 5 to actually get those values to line up. We also do not have a lot of data of the low redshift Lyman alpha forest observationally because we require space-based telescopes to get spectra in the UV at very high resolution. It's very sad. If you ever see a space-based UV telescope and you're on a panel for it, please put in a good word for me, please.
All one of those telescopes you need?
Yeah, or propose some more UV space-based telescopes, please. God, please. Okay, so how do we fix this struggle, this mismatch between simulations and observations? So like I said, you can either get more photons or more heating because the column density scales with both of them. You are going to need more heating than you would need photons, but they both work. So that means rescaling the UVB. At low redshift, it is pretty unconstrained right now, so that's pretty reasonable to rescale the UVB to an extent. And for heating, you might see AGN feedback being a component of heating, potentially stellar feedback can couple to AGN feedback effects and also affect the heating of the Lyman alpha forest indirectly, or maybe cosmic rays, but I won't talk about that because I haven't looked at it. So we can see that just changing the UVB model, looking at illustrious versus TNG, just changing the AGN feedback model, is that what I said? You get a very different column density distribution for the Lyman alpha forest. And you can get basically the same one if you rescale the UVB. So perhaps the AGN effects there are degenerate with the UVB, but it is interesting that you can get a solution with a different AGN feedback model and that the AGN feedback will affect the Lyman alpha forest on these really large scales. So another interesting simulation is the SIMBA simulation, which has a very different AGN feedback model. And you can see that it matches much better than either of illustrious or TNG. If we just go back here, you can see that illustrious and TNG both suffer from a slope issue in the intermediate column density range, but SIMBA seems to have done a much better job in matching that column density distribution. And we can see that it is from the AGN feedback model. So when we remove that, we get that red line, and you can see just how well the AGN jets in SIMBA push down that column density distribution, remove that neutral hydrogen from the IgM, and get something that matches the observations much better. Without the jets, we need a UVB that's 2.7 times stronger, which isn't unreasonable given what we see currently in more modern UVB models, but it is a little high. So realistically, we need updated UVB models and AGN feedback to resolve this discrepancy. So hopefully people know what CAMELS is. What you need to know, oh, 1 minute, oh God, okay. So I use CAMELS to look at varying the AGN feedback effects in SIMBA, so we can vary the momentum flux and we can vary the jet speed. And you can see how it affects the column density distribution. Everybody should use CAMELS, it's a really great data set. And this gives us a much better idea about how the AGN feedback is actually affecting the column density distribution. And we wrote a really nice paper on this. You should go check it out. We also look at the interplay between AGN and stellar feedback. And we are also looking at some power spectrum stuff. So we're looking at the Lyman alpha flux power spectrum with an undergrad that I work with at Rutgers University, Megan Precki. We're doing great work there. Hopefully we'll have more stuff out on that soon. But all of this is to say that the Lyman alpha forest could be a good constraint for AGN feedback models in the future. We might want to consider these statistics when we are constraining AGN subgrid models for these big cosmological simulations. And that is what I have. Thank you.